Hello, this is Yan Fuko from National Taiwan University. 私はカクです。どうぞよろしくお願いします。So this is the course Introduction to Mechatronics, and in this unit we are going to talk about logics. So there are two logics I am going to introduce. One is combinational logic, and the other is sequential logic. And here is the outline of this unit. So combinational logic, I will cover these topics. Digital number representation, boolean algebra, combinational logic design, gray codes, and karnaugh maps. And in the sequential logic, I will cover some frequently used units like latch and flip-flop. So let's go back to the idea. So what is a logic? Why do we need to talk about logic? So logic is actually some circuit that we use to implement some electronic device. Say for example, if we say that we have a water spray that is used to cool down the temperature of some greenhouse. So if the temperature is larger than 30 degrees Celsius, then we turn on water spray to cool down the greenhouse. So this is like a true or false condition. So if this is true, then we turn on the water spray. Then I'm sorry, this is true, T-R-U-E. If this is true, then we turn on the water spray. If it is not true, then we don't do anything. So in this sense, we need this is true-false operation is called logic operation. So in logic operation, we only have like two conditions or output that is true or false. Or sometimes we say it's 0, it's 1 and 0, true and false. And so this is the first reason why we need to learn combinational logic or sequential logic in mechatronics. And the other reason is that in modern computers we use logic to calculate numbers, say that like 0 and 1, things like that. So this is very, very useful knowledge that we need to learn in mechatronics. So what do we do to start this? And so let's first talk about what is the data representative approach, like in the digital way and in the analog way. Okay, so this is like analog computer, digital computer, things like that. So in the digital way, we know the numbers are represented as 0 and 1. Okay, like the logic that we just mentioned. So say that we have a number. This is a binary number. Binary number means you have only two choices. One is 0, the other is 1. So each digit of a binary number is either 0 or 1. And now we have this 8-bit binary number. Okay, you can see this 2. This 2 means it is binary. It is binary. Okay, and so this is the common way that we use in computer. So how do we map this number to the decimal number that we use? Decimal number is the 1, 2, 0, 1, 2, 3, 4, 5, 0, 6, 7, 8, 9, 10. That's the common number that we use. Okay, so this is like 2 to the 0 digit. This is 2 to the 1, 2 to the 2, 2 to the 3, and this is 2 to the 4, 2 to the 5, 2 to the 7, 6, sorry, 2 to the 7. Okay, so each bit is represented like the numbers, the binary numbers that we have here. Okay, so why do we represent number in this way? Why do we use the digital way? Because digital way has what? Has a better approach that when we record it's 0 or 1, that is very clear for the computer. So the advantage of this is that it's less susceptible to noise for computers, or say some recorders. And the other is it's easy to manipulate using computer. But its disadvantage is that it has finite precision. Let's say we have a 8-bit binary number. It can only record a number from 0 to 255. So it has a limited precision or resolution. Okay, that's its disadvantage. Okay, and so there are some sample information that may be loose. Okay, and also, like by contrast, there's the other way to record the data. That's called analog way. So what is analog way? You represent a number, say the pi is equal to 3.141592687. You have infinitely digits for this number. Okay, but problem it is the problem of analog number is that it is susceptible to noise. Okay, a little bit noise will change this number dramatically. Okay, so your accuracy can drop. But the advantage of this approach is that it is exact. If noise is not a problem, then you have infinitely number of digits. Okay, so for the binary numbers, that if you have n bits, each bit is represented 1 power of 2, like this 2 to the 0, 2 to the 1, 2 to the 2. Each of them has a different power. And so in these numbers, say you have a n-bit number, this bit is called the least significant bit, and this bit is called the most significant bit. Okay, those are the terms that we use in computer. Okay, then how do we turn a decimal number to a binary number? Okay, so basically if you have a number 6, you have to say that 6 is equal to 4 plus 2. So what is this 4? 4 is equal to 2 to the 2, and 2 is equal to 2 to the 1. So basically, if you have a 4-bit binary number, let's say if you have a 4-bit binary number, this is bit 1, 2, 3, 4, and bit 1 is corresponding to 2 to the 0, bit 2 corresponds to 2 to the 1, bit 3 corresponds to 2 to the 2, and 4 is 2 to the 3. And you have 2 to the 2, that is 4, so you put 1 here. And you have 2 to the 1, that is 2 over here, you put 1 here. And for the rest, you fill in 0 in those slots. So number 6 in decimal is equal to 0110 in binary. So that's the way that how we turn the numbers from decimal to binary. Okay, so we are very familiar with the decimal system. Now we are going to talk about the binary system. Now, so turning a decimal number to binary number is not so difficult. Now we have to learn more about those binary number operation. So how do we perform the binary number operation? It's called boolean algebra. What is boolean? Boolean is this algebra is invented by a English mathematician. His name is George Boole. Okay, and he invented this operation system, how to manipulate numbers 0 and 1. So there are like only two numbers in this system. Okay, so what is boolean? Boolean is like a truth table operation. So say that you have one variable, that is x, and x can be either 0 or 1. 0 or 1. Okay, and there's another representation of x, that is the inverse of x, or we call it not x. So not x is like x prime or x bar. We call this not x. Not x is the inverse of x. So if x is 0, not x is 1. If x is 1, not x is 0. Okay, and so here we have a map. So what is a map? It's a graphical approach to show the numbers. Okay, using this graphical approach, it's easier to understand those numbers. So here we have x. The value of x can be either 0 or 1. So if the variable x is 0, not x is 1. If the value of x is 1, not x is 0. And this number, this graphical representation is called a truth table. I'm sorry, this is called a map, and this graphical approach representation is called truth table, and this is a map. So we will use both the truth table and the map to understand the number of a Boolean variable, or called Boolean algebra operation. So we have a standard binary operator. So what are standard binary operator? We have one operator is called AND, and the symbol of AND is a dot. Okay, there's another operator. It's called OR, and a symbol is a plus. And there's another operator called exclusive OR, or XOR, and the symbol of it looks like this. That's XOR. So what do they do? Now we have to figure out if the first thing that we want to do is to fill in the truth table here. If x is 0, y is 0, what is x and y? So this is pretty straightforward. Let's finish this column first. If x is 0, y is 0, x and y is 0. If x is 0, y is 1, x and y is 0 too. And if x is 1, y is 0, and this is 0. And if both x, y are 1, and x and y is 1. Okay, so this is how we fill in the value of x and y in a truth table. And also in a map, here we have a map here. So what do we do in a map? Let's check the number. So x can be is a variable, binary variable, so it can be either 0 or 1. Y can be either 0 or 1 too. Okay, so we have x is 0, y is 0. Say these two, they look like input, right? 0 0, and what's the output from these two tables? We have 0 here, so we fill 0 here. So if x is 1, y is 0, x is 1, y is 0, we have 0 here too. If x is 0, y is 1, we have 0 here. And if both x and y are 1, we fill 1 here. So this is the map. So it's just a different way to represent the numbers, okay? The result of a truth table, either the truth table or the map. And here we have x or y operation. So this OR operation, the result is also pretty straightforward. I believe this we learned this in high school already. So what is x or y? We have x is 0, y is 0, and x or y is 0. And if we have x equal to 0, y equal to 1, then 0 1, 0 or 1 is 1. So here n is like both the number has to be 1, both the number has to be 1, and the result is 1. For OR operation, one of the number is 1, the result is 1. So 1 1 1 2. Okay. So here in this in this OR map, x or y, we can also fill in the number. We have 0 1 1 1. Now for the XOR map, XOR is a little bit different. XOR is that only one of the number is 1. The result is 1. Okay, so here we have one number 0 1. One number is 1, so x or y is 1. 1 0. Okay, both here we have two numbers. One of the number is 1. We have 1 here. For the rest of the case, it's 0. This is XOR. Alright, so we have 1 1. The result is 1. So here we can fill in this XOR table. We have 0 1 1 0. So these are the standard binary operators, 3 operators, AND, OR, XOR, and we will use AND or OR extensively. Now, those are the basic rules of Boolean operator. Now we have to move in to Boolean algebra. So what is Boolean algebra? So that's the way that how we manipulate the numbers. So here are the ways to perform Boolean algebra. We have equations, and we write down equations in the normal way. And we borrow the ordinary algebra, the rules from ordinary algebra. It's a little bit different, but we borrow some rules there. Okay. And here, the only difference between the ordinary algebra and the binary algebra is that we manipulate numbers, and the numbers are there are only two choices. It's either 0 or 1. Okay, it's either 0 or 1. Okay. So for example, if we have a Boolean operator, a Boolean variable that is x and y. Okay, we have commutativity. Commutativity means that x this is not plus here. We read this symbol as over, right? So x over y is equal to y over x. X and this is and y is equal to y and x. This is commutativity. And we also have associativity. So this is commutativity. This is associativity. X over y over z is equal to x over y over z. Okay, x and y and z is equal to x and y and z. So this is associativity. And also for another associativity, that we have x. This is distributivity. We have x and y over z is equal to x and y or x and z. Okay, so these are the rules. And also another distributivity is x or y and z, that is equal to x or y and x over z. And here are the axioms of the linear, the boolean algebra, not linear algebra, boolean algebra. And also, here are the two existences of 0 and 1. That is x or 0 is x. X and 1 is x. So, for example, x is either 0 and 1, right? Now, you use 0 to over 0, 1 to over 0. In either case, this is equal to 0, this is equal to 1. So they are x themselves. And here, for example, you have x can be 0 or 1. X and 1, here, 1 and 1. 0 and 1 is 0, 1 and 1 is 1. So they are the same, they are the x themselves. So this is called the existence of 0 and 1. And also x and not x. X or not x. This is not x or x bar. X or not x is equal to 1. Because when x is 0, x not x is 1. If x is 1, not x is 0. So if we use or operator, there will be 1 anyway. Okay, so this is called the existence of complements. And then we also have algebra theorems. So what are algebra theorems? We have x plus x. X or x is equal to x. X and x is equal to x. So how do you know if these theorems are true? You just use 0 and 1 to substitute into this equation. So 0 over 0, 1 over 1. 0 over 0 is 0, right? 1 over 1 is equal to 1. So apparently that these numbers are also the x themselves. Okay, so for this case, you can say x can be either 0 or 1. 0 and 0 is 0. 1 and 1 is 1. So these numbers are x2. So basically, these are theorems. So I'm not going to go through all these numbers, but here you can see that we have idempotent operators, and we also have the absorption operators, and we have simplification operators. These are the important theories of Boolean algebra. And so why the Boolean algebra is so important? Let's do a little bit operation, do a little bit example here. So let me insert one blank page. So we want to give an example. We have electronic door lock. Say if we have door lock and the door has two bottoms. These two bottoms are B1 and B2. Okay, and the door open when the correct combination of the buttons are pressed. That is when B1 is 1 and B2 is 0. So the door open when B1 is 1 and B2 is 0. So you can think about this door open. There's a lock on this door, and there are two bottoms. And the lock of the door, we use a symbol arrow to represent the door lock. And we have bottom B1, we have bottom B2. So the combination of B1 and B2, like these are binary, bottoms are binary. So binary, if the bottom is 0, that means the button is not pressed. So they can be 0, 0, 0, 1, 1, 0, 1, 1. So let me complete this table. And the door is open. That means the lock is unlocked when B1 is 1 and B2 is 0. So this is 1. For the rest of the case, the lock is locked. So this is one example of the Boolean operator. Okay, the real life cases. One of the real life cases that we have to deal with this kind of a problem. Okay, and so that's called the Boolean algebra. Boolean algebra. Now, so what is combinational logic design? The basic idea is that the previous example we mentioned is a combinational logic design. That means the outputs only depend on the current input. That's called a combinational logic. Okay, if the output depends on the previous input or previous output, that's called sequential logic. That's another logic we are going to talk about later in this lecture. Okay, but here we only talk about combinational logic. Okay, so again we back to the electronic door lock we just mentioned. In this example, we have two buttons, V1, V2, and L is the door lock. Okay, and so the door lock is unlocked. Only when B1 is 1, B2 is 0, or say B1 is true and B2 is false. Okay, the B1 is pressed and B2 is not pressed. Okay, so this is a truth table we have. And in the next step, what do we want to do? We want to simplify this truth table. we want to simplify this truth table. That's what we want to do. Okay, we want to express this truth table using the boolean algebra. Okay, using the boolean algebra. So how do we do that? There are two ways to represent a truth table or simplify a truth table using boolean algebra. The first one is called sum of products, and second one that we will talk about is the product of sum. We'll talk about that in a few slides. Okay, so what is a sum of product? Okay, let's see. Sum of product is that so since this is sum of products, you can see that there are many terms that are product terms. Product terms are AND operation, right? So you have these product terms. Those are AND operation, and you have to sum these products. Okay, so you have sum here, sum here, sum here, and this sum operation are OR operation, right? Okay, and you also see like C1, C2, C3, C4. These C's are either 1 or 0. Okay, so now what we want to do is to convert this truth table into this sum of product function. Okay, so your output, that is your L or your Y, is equal to sum of products. So how do we do that? Let's recall the truth table that we have in the previous slide. Okay, so here we have this truth table. What we want to do is that we have 4 rows here, 0, 0, 0, 1, 1, 0, and 1, 1. And we have like V1, V2, right? So here you can see the sum products. We have V1 and V2, V1 and not V2. So this is not V2. And we have V not V1 and V2 and not V1 not V2. Okay? Because we have 2 inputs. So the combination, the number of products is 4. Right? Because we have 2 options for either V1 or V2, right? And that's 2 to the 2, and the number of products will be 4. Okay, so we write them down: V1 and V2, V1 and not V2, not V1 and V2, not V1 and not V2. Okay, and after that, what we can do is we want to determine the numbers of C1, C2, C3, and C4. So how do we determine it? So basically we determine them from this L. Okay, so first we write down the equation Y again, but here we use their number here in this truth table. We have V1 is 1, V2 is 1. That's over here, this column. V1 is 1, not V2 is 0. That is this column. Not V1 0, V2 1. That is this column, this row, and 0 0 here. That is this row. So here we have 1 and 0, 1 and 0. That is 1. So we make C2 1 and the rest of them 0 here, because their output L here are 0. Okay, so we can write down that Y is equal to V1 and not V2. Okay, so this is how we turn a truth table to a equation. or we call this is the boolean algebra. Now we want to introduce the other way to turn a truth table into a equation. That's the product of sums. Okay, so again, for the product of sums, that we need to have sums. So what are sums? Sums are OR operation, right? So we have B1 or B2, B1 or not B2, B1 not B1 or B2, not B1 or not B2. Okay, then we multiply them together. That is the product. So we can see that they are product here. So the products are actually the AND operation. And how do we find the terms, which term we want to keep? So we have to again recall the truth table here. Recall the truth table here. Now we fill in the number just as what we did in the previous slides. If it is B1, we fill in 0. If it is B2, no, if it is B1, we fill in 0. If it is not B1, we fill in 1. Okay? If it is B2, we fill in 0. If it is not B2, we fill in 1. So when we use the product of sums operation, we have to do the inverse. Okay, again, the unbarred variable are 0 and barred variable are 1. Okay, unbarred variable like this are 0. Barred variable these are 1. Okay. Then what term do we have to keep and what term we have to drop? We have to drop the term. The term that the corresponding L is 1 here, like this one. The corresponding L output is 1, and the term the corresponding output are 0. We keep this, and we drop this term. Okay, so here we can see that with B1, B2, 0, 0, 0, 0, right? So we keep it is 0. The output L is 0. We keep it, and we have 0, 1, 0, 1 here. The output L is 0. So we keep this. We have 1, 0, 1, 0. The output L is 1. So we drop this. Okay, and we have 1, 1. The output L is 0. So we keep this. Okay, so the result of the equation is B1 over B2 and B1 or not B2 and not B1 or not B2. So both of the equations, say this is equation 2, and in previous slide this is equation 1. They are valid Boolean algebra equations for this truth table. So both equation 1 and equation 2 here are valid Boolean algebra equations. And we can see that equation 2 is more complicated than equation 1. But this varies from case to case. So you don't know which equation is more complicated and which one is more simple before you perform the product of sums or sum of products. You have to try and see. Okay, and those are the ways to convert truth table to equations. Okay, but as you can see here, like some of the equations can be very complicated, and we want to simplify those complications. And to simplify this complication, there are approaches, and one important approach is called graphical minimization. So what is graphical minimization? We want to reduce the complication of the equations. the complication of the equations. So how do we do that? So since this is graphical approach, we have to perform this on a map. So we perform minimization on a map, not on a truth table. We don't do that on truth table. Okay, so we fill in this information from a truth table to a map, like get these numbers. Okay, and we want to perform the graphical minimization here. So what are these minimization approach? Let's see. We erase all the inks here first. So suppose I change the truth table to this one. So this truth table is different from the previous one. This is a truth table for the current case. Okay. Now this truth table, as you can see, we convert it to a map. So you have 0, 0, 1, 1. Okay. Again, I have 0, 0, 0, 0. We fill 0 here. We have 1, 0, 1, 0. We fill in 0 here. We have 0, 1. 0, 1, that is 1, so we fill 1 here. And we have 1, 1. 1, 1 is 1, we fill 1 here. So for the graphical minimization, what we want to do is to find the adjacent ones. Okay? So what are the adjacent ones? So for example, we have 1 here and 1 here. And they are adjacent. That means they are connected to each other. So once you see adjacent one, you can circle them together, say they are a group. They are a group. Okay? And what does this mean? This means that in the case that V1 is 0, V2 is 1, you have output 1. V1 is 1, V2 is 1, you have output 1, 2. Okay? So like they are basically the same. You don't really care what V1 is. You don't care what V1 is. V1 can be either 0 or 1. And the output is the same. Okay? So the basic idea is that you don't care about V1. What you really care is V2. Okay? So from here, that you can say your output Y pretty much depends on V2. If V2 is 1, your Y is 1. If V2 is 0, your Y is 0. So you can write this equation down. So this is called graphical minimization. And so also the graphical minimization makes sense in a sense that remember the axiom and the theory that we talk about. We have X and Y, or X and not Y is equal to X and Y or not Y. And Y or not Y is total, right? All the cases. So this Y or Y is equal to 1. From the axioms, we have to go back to many slides. Let me do it very quick. Oops, sorry. Let me go back. So you have X or not X is equal to 1. So the same for boolean variable Y or not Y is equal to 1, right? So for the axiom and from the axiom and the theorems, you know that X and 1 is equal to X. So from this table that you know, because V1 not v1 and v2 is 1. So you can write this down, right? Or v1 and v2, because when v1 is 1, v2 is 1 here. This is true, right? And according to the distribution law, that you pull the not v1 and v1 out. Here you have not v1 and v1 out, not v1 and v1 out, and this is equal to 1. So your y is equal to v2. Okay, so you can use the axioms to simplify the equation, but it's better to apply the graphical minimization because it's easier and very straightforward and intuitive. So it's very important to use this approach. So let's see another example. Okay, so if you have a truth table, you have a map like this, how do we do that? Okay, this is basically an XOR problem. Okay, so you can see this and this, that's called XOR problem. You cannot simplify this equation because it's XOR. Okay, so either way, you cannot simplify this. You can have to use either more variables to reduce the problems. Okay. Now we introduce how to simplify using graphical approaches. The next thing we have to do is to extend the graphical minimization to more variables. Now currently we can deal with 2 variables, v1 and v2. So what about if we have 3 variables or 4 variables or 5 or 6? So before we deal with more than 2 variables, we have to learn one more thing that is called gray code. So what is a gray code? It's an approach for record the sequence of numbers. So but it's different from the binary counting approach that we typically use. For example, what is a binary counting way? We see if we have 2-bit binary number, the number changes from 00 to 01 to 10 to 11. And here in the middle, these 2 numbers, like when it changed from this 01 to 10, both the number changes simultaneously, and that is somehow not very stable. We want to change only 1 bit at one time. But how do we do that? We can use the gray code to code this sequence. So what is like a change is for only 1 bit? For example, it's we turn from 01 to 00. You change 1 bit here, and from 00 to 10, you change one bit here. Or you change from 01 to 11. Okay, you only change this bit. Then you change from 11 to 10. You change this bit. Okay. Alright, if we want to do that, okay, we can change the counting order to this. So it changed from 00 to 01 to 11 to 10. Okay, so again, this is the typical binary approach, coding approach, and this is called the gray code approach. And gray code sounds a little bit awkward at the very beginning because you never think about to code a sequence in this way, but it is very useful in this graphical minimization. So what is gray code and what is the binary code? So typical binary code, a 3-bit binary code look like this, and a gray code look like this. So in a binary code, we change from 000 to 001 to 010 to 011, then to 100, 101, 110, 111. But in gray code, you change only one bit at a time, one bit at a time. Okay, so 000 to 001, you change only one bit. And from 001 to 011, you change another bit only again. And from 011 to 010. So basically, you exchange these two, the orders of these two sequences. And now, you from 010, you change it to 110. So you only change one bit. In this binary code, you change 2 bits. Okay, but here you only change 1 bit. And this is 2 bits. And here, you change from 110 to 111. And then to 101 to 100. Okay. So, we are going to use the gray code in the graphical minimization. But how do we generate the gray code? How do we understand? How do we get this code sequence? Here's the approach. You use the reflection to get the gray code. Okay, so what's the reflection? So for example, if you have like a 1 bit, n is equal to 1, okay, 1 bit code sequence, what you have to do is 01. There's nothing to do with it. You keep it. And for 2-bit sequence, you write down 01, and then you mirror it. When you mirror it, it becomes 10, right? 01, 10. This is a mirror. Then you add 0 before mirror, and you add 1 after mirror. So your code sequence becomes 00, 01, 1110. Okay, if you have a 3-bit number, it's the same. You write down this number, this 2-bit number, over here, 00011110, and then you mirror it again. So what's the mirror? Mirror is like these two are the same, these two are the same, these two are the same, and these two are the same. And after you mirror it, before mirror you add 0 in the 3rd digit, and after mirror you add 1 as the 3rd digit. Then you get this perfect gray code. So this is how we obtain the gray code. So why do we need gray code? Because in the graphical minimization, we want to code the sequence adjacent numbers in gray code. It helps us to find and minimize boolean algebra equations. Okay, that's the reason. Okay, so for example, if we have 3 bottom door lock, our bottoms are B1, B2, B3. Now we have 3 bottoms. And our output, this is input. And our output is a door lock. I'm sorry. Wrong spelling. A door lock. Arrow. Okay. And how do we do the graphical minimization? We want to sequence. We want to write down the truth table first. So in the truth table, we have B1, B2, B3, B4. And then we want to convert this truth table to the map. And in the map, we sequence B1, B2 together in one dimension. So this dimension is B1, B2. And in another dimension, we sequence B3. So B1, B2, and B3. But in the coding of B1, B2, we use gray code. That means we have to write down the gray code for n is equal to 2. That is 0, 0, 0, 1, 1, 1, 1, 0 here. And B3 is 1 bit, so you write down 0, 1. That's pretty straightforward. And then you copy. I'm sorry, I made another mistake. This is not B4. This is L. You write down the L number inside this map. Then you can do the graphical minimization. Okay, and this approach is called karnaugh map or K-map. K-map approach for graphical minimization on the boolean binary equations. Okay, so how do we do that? We write down the gray code here. In this example, and then suppose we have a truth table and we fill in the numbers here. So how do we minimize this map? Remember what we have learned previously. We have to circle the adjacent ones. So you have 1 here as adjacent 1, right? And what do you have? You have 1 here as adjacent 1. And also you have 1 here as adjacent 1. Remember this one. Don't miss it. Okay, so you see that there are 3 adjacent ones. Okay, so what is your output y is about? You have output y, that is 1 when B1 when B2 is 1, like these two together. You don't really care about B1 because B1 either B1 is 0 or B1 is 1. The output is 1, right? This is 1 only when B2 is 1 and B3 is 0, right? So B2 is 1 and B3 is 0. That is not B3, right? So this circle is equal to this B2 and not B3. And what else? What else 1 do we have? We have 2, 1 here. And what do they correspond to? They correspond to B1 is 1, B2 is 1, B1 is 1, B2 is 0. So in this circle, you really don't care about B2 because it can be 1 or 0. You care about B1. B1 has to be 1. So B1 has to be 1. And B3 has to be 1, 2. B3 has to be 1, 2. So that is about this circle. What about this circle? This circle has 1, 1 here. That in these two codes 0, 0, 1, 0. Their common is they have B2 as 0, right? So these two, the output is 1 only when B2 is 0, that is not B2, and when B3 is 1 and B3. So from this map, and we use karnaugh map approach, we can determine the output y is equal to B2 and not B3, or B1 and B3, or not B2 and B3. Okay, so let me clean the screen. So basically, you use sum product form. If you write down this one, what is that one? That is b1, not b1 because it's 0, b2 and b2, and not b3, right? And then you write down this one. What does that equal to? It is equal to b1 is 1, b2 is 1, and b3 is 0. So it's b1 and b2 and not b3. And again, you have another one here. It is all the three b1, b2, b3 are 1. Okay, so you have b1 and b2 and b3. And we write down another one here. That is b1, not b2, b3. b1, not b2, b3. And the last one over here, 1 is not b1, not b2, b3. Not b1, b2, b3. Okay, and you say, alright, this is the typical way that we have. But this sum product form is complicated. And how do we simplify it? We use this axiom that we talked about before. X and y, or x and not y, is equal to x. So here, for example, you have b1 and not b1, but the b2 and not b3, b2 and not b3 are in common. Those are in common. Right? So you can simplify this term by putting them together. So this will becomes b2 and not b3. Okay? So for the same reason, in these two products here, you have b1 and b2 and b3, b1 and not b2 and b3. So the common are b1 and b3, but we have b2 here and not b2 here. So these two can be cancelled to each other. It will become b1 and b3. And the last one, this circle, is b1, not b1, not b2, b3, and b1 and not b2 and b3. So the only difference here is this b1 term, and you cancel that out. So you have b not b2 and b3. So this is why the Karnaugh map works, and how do we turn a sum product form into a simplified form. Okay, and I hope that is a clear enough example. We want to make another example here again. So for example, we have a case here that the door lock, but now the map looks like 0, 1, 1, 0, 0, 1, 1, 0. Okay, in this case we see adjacent 1. Okay, but they are adjacent in both directions, in the b1 b2 direction and in the b3 direction. So here when we circle them, we can circle them like this. So what does it mean? Here we have this one, the four ones together. They don't really care about if b1 is 0 or b1 is 1. They don't really care about if b3 is 0 or b3 is 1. It only cares about if b2 is 1. So for the example, you can say your output y is equal to b2. This is straightforward. Okay, so that's another simplification method in the Karnaugh map. Alright, now let's move to more complicated cases. The next case is that what if we have four variables? Now currently we have b1, b2, b3. What about we have a b1, b2, b3, and b4? So for the four variables, we can still use the Karnaugh map. So what we have to do is we put v3 and v4 together in one dimension, and we also code them as using the gray code. Okay, so v1 v2 is gray code 0 0 0 1 1 1 1 0, and v3 v4 is 0 0 0 1 1 1 1 0 2. Okay, so in this example you can see like if we write down the map from the truth table, we can circle them together. So for example, we see that there are 4 ones here, so you can circle them together here, and we have 1 1 here, we can circle them together too. Okay, and we have 1 1 1 1 here, right? So you can circle them together. Let me use another color so it'll be more clear for you. So if I use another color, let's use green for this one. Let me erase it, it's not very clear. If we use green for this one, and if we use say blue for this one, so for this 1 1 1 1, what do we have? We have our output L, that is equal to what? In these 2 bits we don't really care about v1, right? We care about v2. v2 has to be 1, so we have v2 here. And in these 2 bits we don't really care about v4. v4 can be 0 or 1, but v3 has to be 0, so it is v2 not and not v3. That's the red circle. So what about the green circle? In this green circle, we don't care about v1 because v1, I'm sorry, we don't care about v2 because v2 can be 0 or can be 1, but v1 has to be 0. So here we put an OR operator here, and the v1 has to be 0. So it's v1, it's not v1, and v3 has to be 0, not v3, and v4 has to be 1, and v4. And what about this blue circle? In this blue circle, we don't care about v2 because v2 can be 1 or 0. We care about v1. v1 has to be 1, so we have v1 here. And we don't care, needs to be, we don't care about v3 because v3 can be 0 or 1, and v4 has to be 0. So in this blue circle, it is v1 and not v4. Okay, so this is how we do the karnaugh, using the karnaugh map approach to do the graphical minimization on 4 variable case. On a 4 variable case. So you have the results here. Now using karnaugh map, you can solve problems up to 6 variables, v1, 2, 3, 4, 5, 6, because you can probably write down a 6-dimension graphic maps. But if your variable is more than 6, you probably cannot do this using the karnaugh map. And there's one more thing we have to talk about, that is don't care. So what is don't care? Because sometimes you don't really care what an input is. That's a physical condition. It doesn't matter, or it doesn't exist. And we, in that case, we put don't care here. Because it is don't care, so you can actually circle, you consider don't care as 0 or 1. In either case it works. Okay, so in this don't care case, here you can see that we have b1, b2, b3, b4, but we have don't care circle over here. No, a circle that you have 1 don't care here, because it can be 1 or it can be 0. It doesn't matter. And also you can circle another 4 ones here. Okay, and you can circle another 2 ones here. So this pretty much complete your karnaugh map circles. And so how do we determine this circle? What does it mean? Your arrow, let me change color, is like in b1, b2, the b2 can be 0 or 1, so you don't care about b2, you care about b1. Your b1 has to be 0, so it's not b1. Okay, and here you don't care about b4, you care about b3. b3 has to be 0, so it's not b3. So the blue circle corresponds to this not b1 and not b3, and the red circle corresponds to what? You have you don't care about b1 because it can be either 0 or 1, but you care about b2. b2 has to be 1. Oops, sorry. Let me erase it. You care about b2. b2 has to be 1. And you don't care about b4, and your b3 has to be 0. So it's and not b3. Okay, that's the red circle. And what about this green circle? You don't care about b2 because it can be either 1 or 0. So you care about b1. b1 has to be 1. And your b3 has to be 1. And b4 has to be 0. So this is the simplified Boolean equation from this karnaugh map. Okay, so if you have a don't care case, that you basically you can consider it is 1. Okay, and after we learn how to simplify the Boolean logic using karnaugh maps, next step is to understand how to implement those Boolean logic using circuits. And before that, we have to learn what the pseudo circuit. So what is a pseudo circuit? Pseudo circuit is a way to plot those Boolean equation into a circuit, and those circuits are not true circuit. The true circuit is like the IC circuit, you put them together. But pseudo circuits are symbols, and symbols are simple, so you can understand them more easily. So what are pseudo circuits? Here you can see, like we call them gates. So we have OR gates, it's like this shape, and we have AND gates, it's like this shape, and their truth table are the same as we just shown before. And we also have NOT gates. NOT gates is basically invert. So if you have input X, output Z, and if the input is 0, output is 1. If the input is 1, output is 0. Okay, and also if you put a circle in the tip of the OR gates, it's called NOR. So this NOR is is not OR. So it's called NOR. Okay? And if you put a circle in the tip of an AND gate, it's called NAND. So this NAND is not AND. So not AND is just the inverse of AND. And not OR is just the inverse of OR. So the outputs are inverse. The outputs are inverse, as you can see here. Okay, so in the next step, we want to plot these circuits, these Boolean equations, or say implement those Boolean equations using the pseudo circuits. This is what we want to do. So how does the pseudo circuit work? Let's make an example first. Okay, if we have a 2 to 4 line decoder, so what is 2 to 4 line decoder? That means you have 2 inputs, you have 4 outputs. Okay, and in these inputs, they are binary inputs, so they can be either 0 or 1. Those are the input bits. And output also the same, they can be 0 and 1. This is the output. Okay, and the 2 to 4 line decoder, the output is 1 only if the corresponding number of the input is 1. What does that mean? So you have like a 2-bit input number, I0, I1, right? And let's say if Y2 is 1, only if this number is equal to 2. So this number, I1, I2, can be there can be possibilities on this number. There can be 3, 2, 1, 0. If I1, I0 is 1, then your I1 is equal to 1. If your I1, I0, this number is 0, then your Y0 is 1. If the combination of these two is 2, then your Y2 is 1. Combination of these two numbers is 3, your Y3 is 1. Okay, so as you can see here, you have a truth table that state their relationship. So how do we implement this circuit? So this is a very simple circuit. The logic is very simple. So we don't really need to use karnaugh map or the previous simplification approaches. What we have to do is to check their combination. So let's say your Y0 is 1 only if when I1 is 0 and I0 is 0, right? So I0 is 0 and your I1 is 0. Both of them have to be 0, and your Y0 is 1. Okay, so what about Y1? Y1 is 1 only if when I1 is 0, I1 is 0, and your I0 is 1. I0 is 1. Okay, and what about Y2? Y2 is 1 when I1 is 1, I0 is 0. I1 is 1, and I0 is 0. Okay, and Y3 is 1 only if when I1 is 1 and I0 is 1. So both of them has to be 1. Now if you use 2 NOT gates and 4 AND gates together, you can create a circuit that is 2 to 4 line decoder. So that's the reason why we have to learn about pseudo circuits, because we want to implement these 2 to 4 line decoders using the circuits. Okay. So before moving to next topic, we want to remind some of the boolean algebra that we learned in high school. It's called De Morgan's law. So in De Morgan's law, it says that the NOT of x or y is equal to the NOT x and NOT y. And also, NOT x and y is equal to NOT x or NOT y. So this is called De Morgan's law. And De Morgan's law is used to convert gates from AND over to NAND NOR. In the sense that if you want to implement the circuit using NAND or NOR gates, you can use De Morgan's law to convert these. Okay, so if you have like one OR case, and if you want to convert it to a NAND, this is a NAND gate, right? This is OR gate. You can use De Morgan's law. And if you want to convert an AND gate into a NOR gate, you can use De Morgan's law. And why do we want to convert an OR gate or an AND gate into a NAND gate or a NOR gate? Because these two gates are more available. They are more available. Okay, this is because the design of the circuits, the TTL, CMOS, the reason of that. So this is very useful in the field, but in theory we don't really need to use the De Morgan's law. But this is just for your information anyway. Alright, let's see another example. Now in this example, it's called excessive 3 binary coded decimal. So what is this? That means we have inputs. Inputs can be a decimal number from 1 bit decimal number from 0 to 9, and the output is a decimal number, and output is equal to the input plus 3. So if the input is 0, the output is 3. If the input is 1, the output is 4. Okay, such as you have 2, 5, 3, 6, and 9, 12, like this. And this is called excessive 3. Excessive 3. So how does it work? How does it work? What we want to do is we want to create a truth table of this problem. And after we create the truth table, we want to convert it into a map. And then after that, we want to implement the map, the simplified Boolean equation using the pseudo circuits. So we want to solve this kind of problem. Okay, so let's think about this problem. if we want to a input that can represent 10 decimal numbers, how many bits do we need? Because in boolean algebra, one bit can be either 0 or 1, right? So actually, to represent 10 numbers, we need 4 bits. We need to use 4 bits, 4 binary bits as our input. Why is that? Because if we have only 1 bit, we can represent 2 numbers. If we have 2 bits, we can represent 4 numbers. If we have 3 bits, we can represent 8 numbers. And if we have 4 bits, we can represent 16 numbers. Now we have 10 numbers here, so we need 4 bits. And the input bits, now we make it A, B, C, D. And output bits, we have to represent 12 numbers. We don't care about 0, 1, 2, but still we need to represent 12 numbers. And for the output, we have to use 4 bits too. So basically, we have A, B, C, D as the input, W, X, Y, Z as the output. Now, in this problem, we want to find the map between A, B, C, D and W, X, Y, Z. That means we want to understand how to, I'm sorry, this is not A. How to represent W using A, B, C, D, and X and Y and Z. Okay, so we want to solve this problem. And after we solve that problem, we want to implement the pseudo circuits to draw the circuit diagram. Okay, so let's move to next step. The next step is to come up with the truth table. So in this truth table, the input, we have 10 numbers here, and their inputs A, B, C, D corresponding numbers are written down over here too. And for the output, we have W, X, Y, Z, 4 bits, the same as the previous slides what we talked about. And their corresponding number corresponding to 3 to 12 are here. And after we complete this step, what we can do, we can write down the karnaugh map. So what karnaugh map do we have to write down? We have to write down the karnaugh map for, say, W. Okay, so let's see if, we start from W. We have these W numbers, right? And we have A, B, C, D, these numbers. So the A, B, C, D are inputs. So we write down A, B in this dimension, in that direction. Oops. And CD in this direction, AB in this direction. And here, they are coded as gray code 00011110. The same for the CD. Okay, and next, what we have to do is to write down their corresponding number of W in this truth table. For A, B, C, D is equal to 0, 0, 0, 0. We write the W is 0, and so we write that 0 here. For A, B, C, D is equal to 0, 0, 0, 1. W is 0. So 0, 0, 0, 1, 0 here. So we write them down one by one, one by one. Okay, so we write down all the numbers in W here in this column. So we totally have 10 numbers. What about rest? The rest we don't really care because we don't use them. For example, if ABCD is equal to 1, 1, 1, 1, we don't have 1, 1, 1, 1 here, right? Oh, sorry. We don't have 1, 1, 1, 1 here. So we don't really care about what W is. So we write down don't care. Now we have a very nice map here. And next thing we have to do is use the graphical minimization approach, or say the K-map approach. And what do? We circle the ones together. So in a sense that we have, say, adjacent 1 here, or don't care here. And also, let me change the color so you can see it better. We have adjacent 1 here, and also we have adjacent 1 or don't care here. So 3 circles, and each circle has their corresponding boolean algebra, and we want to write them down. So for example, for the red circle, we know that W is equal to, in this circle, we don't care about A because it can be either 0 or 1. We care about B, B has to be 1. And we don't care about C, and D has to be 1. So it's B and D. And for the blue circle, has to be it doesn't care about the A, the B has to be 1, and it doesn't care about D, but C has to be 1. And also for the green circle, that very big one, it doesn't care about B, but A has to be 1. And it doesn't care about C or D. So this equation basically is the simplified Boolean equation that we obtain from this K-map approach. So let me erase all the inks. As you can see, so this is the equation that we have. Okay, and we can do this for X, this X, and also Y and Z, and obtain their equation. So I'm not going through all the equations, but as you can see here that this is the result from the K-maps. So the next step is that we obtain their equation W, X, Y, Z. And the next thing is that we can implement these equations using the pseudo circuit. So for example, we know that W is here. W is A or, and here I'm not going to the detail of this pseudo circuit, but you can take a look and understand how it is implemented. Now since we have we can actually implement the circuit, the Boolean algebra equation using the pseudo circuit. We basically have to understand how this pseudo circuit interface one from another. What does that mean? Because if we want to implement some circuit using those gates and or not gates, we want to understand how they work with each other. Because in the Boolean algebra, we have 0 and 1, and in circuits we have like 0 is equal to low and 1 is equal to high. But what is low and what is high, we have to make it clear. And so this is how we how the components they work. So basically, if we want to say 1 voltage is a low voltage, we have to say that the range of this low voltage is less than 0.4 volts or 0.5 volts, and it has to actually between 0.8 and 0.4. And for the high voltage, it has to be larger than 2 volts. Okay, at least larger than 2 volts. So before this is high volts, or say 1, and below this it is low volts, or say 0. Okay, so when we put the components, the gates, the physical gates all together, you have to understand how they work with each other, and this is how they work with each other. Here you can see the 74 family TTL parts, and this is the issues they have to consider. But how do they actually implement it? Those gates are implemented using the BJT or the CMOS components that you learned in the previous unit, to a previous chapter. So let's make an example. If you have like dials over here, your X and Y are inputs. Let me change another color. These are inputs, and Z is the output, right? And how do you actually make the this gate work? Let's see if this is an AND gate or is an OR gate. If X is high, that's for example, if let's use 0 and 1 instead. If X is 0, is low, Y is low, how does it work? If X is low, Y is low, the current goes through from VCC to X to ground, right? So basically your X is connected to ground, your Y is connected to ground. Okay, and the Z is what? Is connected to ground. So your Z is 0. Is low actually. And if your input X is 1 is high volts, alright? So your X is connected to 5 volts, to connected to VCC, high volts. And your Y is still connected to ground. So how does it work? Still the current flow through VCC to Y, so your Z is still connected to ground, so your Z is 0. And what if it is high-low? It's 0 too. So what if it is high-high? When both of the X, Y are connected to high, connected to VCC, in a sense, X, Y are connected to VCC. Let me erase this one. To X, VCC to Y. Now there's no current flow through VCC to X or to Y. Your Z is actually high. So if this is 0, 0, it's 0. 0, 1 is 0. 1, 0 is 0. 1 1 it is 1. So this is like it works like an AND gate. For the example on your right hand side, here you can see, if you write it down, it's low, high, high, high. If you go into the detail, then it works as an OR gate. Okay, so by using those diodes or transistors, you can actually make them. You can actually manufacture some AND gate and OR gate. Okay, and those diode gates doesn't work very well. Okay, so basically that's the reason why we use the RTL, the resistor to transistor logic gates. Those are invented later. So I'm not going to the details, but you can see this is a NOT gate, NOR gate, and this is an AND gate. And the same for the resistor to transistor logic, RTL, it doesn't work very well either. And later on, we invented transistor to transistor logic, okay, TTL. So this TTL is actually a NAND gate. So I'm not going to the details here. This is a NAND gate transistor. And AND gate transistor is actually a NAND gate at an inverter. Okay, so actually it works like AND gate is equal to NAND at a inverter. That's the reason that I say this NAND gate is more available. Okay, so this is the TTL gates. And so how does the TTL gates work with each other? You need to understand their specs. And here are the specs of the 74 families. To use these gates, you have to understand their low level input voltage, output voltage, high level input voltage, output voltage, and the input current, output current, and how much current they draw, how much energy they consume. Okay, they are for different purposes, and their propagation delays that we will talk about later. So this is a table for your reference. And so for the 7400 families, how do they look like? They actually look like this. One gate, one chip doesn't come with only one gate. They usually come with 4 gates or more. Okay, so here you can see if you have a 7000 NAND gate, like you have 4 NAND gates here, and you can see like this pin 12, 13, they are input pins, and this pin 11, they are output pins. And here the same for 9 and 10, they are input, 8 is output. And you have input here, output here. And you have input here, output here. And the chip also need a VCC and a ground to supply the power so it can work appropriately. So it comes with a 14 pins in total. And it's the same for the NOR, XOR, AND, OR, and inverter gates. But for the inverter, because you only need 1 input pin and 1 output pin, so for one chip it comes with 6 inverters. So for the boolean circuit diagram, here you can see from the previous door lock example. Remember our door lock example? That's back to many slides ago. That we have the door lock output is equal to V1 and not V2. So how do we connect it? So the pseudo circuit looks like this. We have V1 and not V2. So we use an inverter on V2. And V1 not V2, the result is the L. But in the actual circuits, we don't have we can use NOR gate to implement it. So we use De Morgan's law. Remember De Morgan's law? We can use one inverter and one NOR gate. This is a NOR gate and this is an inverter to implement it. And okay, and as you can see, the inverter is 7404. The NOR gate is 7402. So we have an inverter here. We have a NOR gate here. So what we want to do is that we connect V1 to the inverter to pin 1. That's the input. The output is Y1. So this is no, I'm sorry. The pin 2 is the output. This is pin 1 of the inverter. This is the pin 2 of the inverter. And we also connect the output of the inverter, that is pin 2, to the pin 2 of the NOR gate. So we connect this pin all the way to this output over here. And another input is from V2 directly. So we have V2 over here directly connected to pin 3. And so this is the inputs of one NOR gate. The output is pin 1 and it is L. So this is the pseudo circuits and this is the physical circuits. Okay, and that's how we actually implement the circuits. And now let's talk another technology. Actually, another gate that is composed of CMOS gates, CMOS components. So in the previous slides, in the previous chapter, now you learn about CMOS. So how do we build a gate using CMOS components? Now here we have an example. We have in this logic gate, we have 4 CMOS components: Q1, Q2, Q3, Q4. Now suppose you make X and Y low. So when X is low, this Q3 is off. When X is low, Q3 is off. And Q1 is on. Okay, Q1 is on. So you can see that the voltage source VDD goes through Q1 to Z. So Z actually is high. Okay. Now, when Y is low, this Q4 here is off too. Okay. And Q2, the Y connected to Q2 through this line. This Q2 is on. So it's the same that the VDD is connected to Z through this path. Okay, so this tells us if one of the X or Y is low, then your Z is high. Okay, if one of X or Y is low, your Z is high. One of X, Y is low is high. What if both X, Y are high? If both X, Y are high, that the Q1 and Q2 are off, but Q3, Q4 are on. Right? So both Q3 and Q4 are on. Your Z is connected to ground. So your Z is low. Okay. And so what is these gates? Forget about this Q1, Q2, Q3, Q4 in the middle. When X is low, Y is low, your Z is high. X is low, Y is high, your Z is high. X high, Y high, low, Z is high. and if both x, y are high and your z is low. So this is basically an NAND gate. Okay, so this is how a NAND gate built using the CMOS components. And here we have the characteristic of the CMOS family. So I'm not going to the details of this table. I will leave this to you. So just take a look. And so how do we actually interface the CMOS with the TTL? So basically there are two families, transistor to transistor logic and the CMOS, the MOS logic. And can we interface them together? Because they are different components. Can they work together? Some of them work together well, okay, but some others you need additional condition, like the C here. You can see the notation in the very bottom of the slide, and the B here and A here. Okay, so you have to understand what chips, what gates you are using, and what family it belongs to, and if one gate can work with another gate. Okay, so just check this table. Okay, now in the previous slides we talked about that if we want to use logic gates, we have to know that they are made of different components, like a TTL component or the CMOS component. And one thing we have to realize that this component, they works. When they works, there's a delay. What do I mean by saying there's a delay? So suppose that you have a gate over here and you change the voltage of the input. And does the output voltage change simultaneously? No, it doesn't. It takes some time. It takes some time to change the voltage. Say if your V in goes from low to high. Okay? And what about your V out? It takes some time to go from high to low. Say this is an inverter. Okay? So when you implement an inverter, when the input is high, the output is low, right? So your input change from low to high, and your output is supposed to change from high to low. And here we see that there's a change. Okay, but there's a delay. There's a delay. This is called TP, high to low. Okay, and when your input change from high to low, you change the input simultaneously. I mean, instantly. Then does the output change simultaneously? No, it doesn't. There's a delay too. Okay, because these components are made of materials, and these materials takes time to work. Okay, so this delay is this propagation time is called TPLH. It's called propagation delay. Okay, so there's a P there. So what does it mean? That means that the components takes time to work in the real world. It doesn't work simultaneously, instantly. So you have to consider this propagation delay. If you don't consider the propagation delay, there will be problems. There will be problems. Okay. So what problem can we encounter? Let's make an example here. So this kind of problem, we call them glitches or hazards. Okay. So let's recall one example that the log example we have previously. So in this log, door log example, we have 4 inputs, B1, B2, B3, B4, and we arrange the B1, B2, B3, B4 both in the gray code sequence. So these are the gray code sequence, and then we create this map for the door lock. And now in this map we can simplify the output logic, right? Remember how we do that? We circle them, group those adjacent ones. So we see that there's an adjacent one, and there's another 4 adjacent ones, and there's another 2 adjacent ones. So we write down the simplified logic, and then we can implement this logic using the pseudo gates. So this figure looks like this, right? And now we want to implement one change in your inputs. Now say in this example we want to change the inputs V3. Okay, so how does the V3 change? You can see that at this time, at this moment, the V3 changes from high to low. Only the V3 change, the V1, V2, and V4 remain high. Both of them are high. They are always high. Okay. So what does this change mean? Basically, you change from high, 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 high. What is high, 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 high? That is this state. This is high, 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 high. Change from high, 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 high to high, high, low, high. That is high, high, low, high. High, high, low, high. So you change from this state to this state. Okay, and supposedly, I mean ideally, that these are both makes the door output arrow, door lock output arrow high. There shouldn't be any change. Okay, that means ideally your door lock should remain high, because these two states are both circled in some adjacent ones. Okay, you change from this green state to this gray state. What does that mean? This makes your output arrow high, right? This also makes your output arrow high. So the door lock should remain high, always remain high. But it doesn't work in that way. Why is that? Let's take a look of these pseudo circuits. You can see that in this V3 circuit, not V3, in this circuit, when we change the V3, how does this state, this gray state change? This is V2 and not V3. V2 and not V3. It takes two gates to propagate that V3 signal to V2 and not V3. You have to go through one inverter, and then you go through another AND operator and circuit. Okay, it takes like two logic gates to reach this state. However, for this green state, it's you only need one logic gate to change it. So this is V1 and V3 and V4 is over here. V1, V3, and V4. So when you change your V3, okay, this change happens faster. This change happens faster than this change. This is slower. This is slower. Okay, so let's take a look of the timing diagram. Let me erase this first. Okay, so what happened here? In this state, now the V2 and V3, the V2 and not V3 here. The V2 and not V3. When you change the V3, it takes longer time to make it happen, right? But for this V1 and V3 and V4, it takes shorter time to make it change. Okay, so after this V1 and V3, V4 change, and before this V2 and V3, V2 and not V3 change, you see there's a window. In this window, your door lock goes from high to low. In this window, your door lock goes from high to low. Okay, and that is a glitch. That is because due to the propagation delay, the door lock go to unlock state, and this is something that you don't want. Okay, so you press the correct button, you're supposed to lock the door safely, but there's a problem that even the combination of the inputs are correct, the door still unlocked. That is something that you don't want. Okay, so this is like the propagation. This is a glitch due to propagation time. So what can we do about this? Okay, what can we do about this? We know this propagation time causes this glitch, and this is very common. Okay, and how do we prevent it from happening? Okay, let's see. We know that this glitch happened because you change from this state to this state, right? Let me erase it. From this state. Now what you can do is you create one more state that includes both of these red circle ones. Okay, that is V1 and V2 and V4, this gray color. Okay, you increase this one. Okay, then your circuit design, you increase one more product term over here, and this product term goes from these circuits. Okay, so when you implement your circuits, okay, you have one more term, that's V1 and V2 and V4. So your door lock remains unlocked. Your door lock remains unlocked. So when you consider to implement the logics using the gates, you have to consider the physical propagation delay caused by those gates. And in your circuit design, you have to consider this situation to prevent the glitches. This is very important. Now we have complete the talking of the combinational logic. We have to move to next unit, that is sequential logic. And in this sequential logic, I will just briefly talk about some commonly used logic gates, and I'm not going to talk about too much details because we don't have much time. And before I move on, I have to talk about again what's the difference between combinational logic and sequential logic. So we learned that what combinational logic is, and we learned that how do they work. Like in combinational logic, we know it's a circuit. The circuit maps from the input to the output. So combinational logic is a circuit. And in these circuits, we map the input to the output. Okay. And what is a sequential logic? What's the difference between these two? So in sequential logic, it is a circuit too. But the difference is that the circuit considers both the input and the previous output. And come up with a new output. Okay, so this is the sequential logic. It considers the previous status. So why do we need to know the previous status? Say, for example, if you have a clock, so how do you count the clock, the seconds? You have to understand what is the previous seconds, and then you add 1 to next seconds. And that's the reason why you need to understand or to consider the previous output. And so this is a difference between combinational logic and the sequential logic. So that makes it more clear here. So in a sequential logic, you not only consider the current state, you also consider the previous state. Okay, I'm sorry, this is the current state and this is the previous state. You consider both of them and use them to generate your outputs. Okay, so if you have learned about the automatic control, you know this kind of approach is also called feedback signal, because you have the feedback from previous states. And both of the current state and next state determine your outputs. And you can see that basically you still need to have a combinational logic circuit here. And you also need another combinational circuit here. And both of the combinational logic works together to make this become a sequential logic. Okay, this sounds complicated, but we'll go into one very simple example later. And these sequential logic components, we also call them memory devices, because as what I just said, that these circuits, they consider the previous status. So basically it likes that it works like that. You have some previous states. Okay, you have to remember those previous states and use those information and to come up with a current state output. So basically you can say that they store the previous states. That's your memory. Okay, so what do we use to store device? I mean, what memory device do we have? Here basically we have latches. We also have flip-flops. Okay, so what's their difference? Basically latches, they don't work with clock, but flip-flops, they work with clock. So you, like a computer, you have a system clock to make it work. So this is with clock. This is without clock. Okay, and for both of the devices, we have 4 types. We have 4 types of function. We have set function. What is set mean? You make the output high. And we have reset function. That means you have we make the output low. Okay, and there's a toggle operation. Toggle operation means if the output, the previous output is high, you make it low. Okay, let's forget about the previous. If the output, the previous output is high, you make it low. And if the previous output is low, you make it high. So this is toggle. Toggle is previous output is high, you make it low. If the previous output is low, you make it high. That's called toggle. And also there's a function, no operation. No operation. Okay. And based on these functions we need, we come up with 4 types of memory devices. We have SR type, we have T type. SR type is set and reset. T type is toggle. And we have D type, that is data or delay. You basically only store those information in this memory device. Or there's JK device. JK is SR plus toggle. So let's let me see. Let's just move to slide number 47, the SR latch. So let's go back to 45. We have these 4 types of devices, and these devices are like SR latch, SR flip-flops, T latch, T flip-flops, D latch, D flip-flops, and JK latch, JK flip-flops. So SR latch is the most simple device, and we are going to talk about this SR latch first. So as what I just explained, so what is the function of the SR latch? Basically what we need is to make the output set or reset. So your output, this latch have to you are able to change the output to make it low or make it high. Okay, and this SR latch is composed of 2 NOR gates. As you can see in this figure here, it is composed of 2 NOR gates. Okay, it has 2 inputs. One is R is reset, and the other is S is set. And it has 1 output, but it also has the complement of the output, or not the output. So the output is Q, and also we have not Q here. Okay, so what does this supposed to work? Okay, if your set is 1 and your reset is 0, you want set the output, right? So your output is supposed to be 1. Okay, and if your output is 1, the not output Q, not Q, supposed to be 0. And if you have 1 in your reset input, then your output should be 0, and the not output, not Q, should be 1. Okay, but what if both the R and S are 0? This memory device is supposed to remember the previous status, so your Q has to be the previous status. That is the Q and Q prime. So it keeps the information, the status of the previous status. It doesn't change. Okay, that's the purpose of this latch. This is the very special thing, and this makes the sequential logic circuit different from the combinational logic. So we have Q and Q prime here. Okay, and based on this information, we also have to figure out what if both R and S are 1. If both R and S are 1, this is called not allowed, because it doesn't work. Okay, so this is called not allowed. So this is basically what a SR latch is. It's a set reset latch. You can use both the inputs R and S to manipulate the output Q. Okay, and using these 2 bits to control your output Q. And so how does it work? How do we include like the previous states in this latch? What we have to consider? Let's come up with a truth table. Okay, so this truth table only talk about the current status. Right? If we want to come up the previous status, okay, we have to use this truth table. So in this truth table, this is the previous status, and this is the current status. So you have a Q star. Star means this is the current status. Okay, so now we have a truth table, original truth table with R and S as the input, right? So we have 4 cases. But if we include the previous status here, we have 8 cases in total. So what if R and S are 0 and your Q is 0? Your previous state's Q is 0, so your current status is 0 too. Because here we can see that this SR latch is supposed to keep the output the same as the previous output when your R and S both are 0. Right? And if your previous state's Q is 1 and R and S both are 0, the current output should be 1. Okay? And what if your R is 0, S is 1, and previous status is 0 or 1? It doesn't care about your previous status because you set the output, right? So your current output should be 1. What if your reset is 1 and sets are 0 and previous status are 0 or 1? It doesn't care about your previous status. It cares about your reset. Okay, so the output should be 0. And this is when both R and S are 1. This is not allowed. So we have these numbers here. Okay, now once we come up with this number, then we can use K-map, and then we can later determine the function of this SR latch. So what we have here, we have RS, the 2 inputs here, and we have the previous output Q here. And then we fill this K-map using the truth table that we just generated. Let me clear the screen. Okay, so 0, 0, 0, 0, 0, 0, this is 0, 0, 1, 0, 0, 1, 0, this is 1 here, 1, 1, 0, 1, 1, 0, this is no care here, 1, 0, 0, 1, 0, 0, it's 0 here. Just such as you fill in the maps with the information here. Okay, and you know what to do next. Use the K-map approach, karnaugh map approach, to simplify this K-map. So what can we simplify? Here we have 4 adjacent ones here and 2 adjacent ones here. So you come up with a logic that your current output is S over Q and not R. Okay. Now this is what I want to point out, that the current input depends on the previous input, because your current output this should be output, because your current output Q star depends on your Q. So this is basically why we call it memory devices. So this is an SR latch. So what's the difference between latch and flip-flop? We have another example. It's called SR flip-flop. So the function of the SR device are the same. The only difference between flip-flop and latch is that in the flip-flop it includes the system clock, this CL here. So you have to consider the system clock, because the system clock is like generated at a fixed frequency. So when the frequency changes, or when the clock changes, your output has to change too. Okay, so it works like this. Now we have three inputs: your R, S, and CL, R, S, and CL, and your clock can be clock input are these high-low square waves, and they change at a fixed frequency. So this is CL clock. Okay, and your clock input can be high, that is 1, and can be low, that is 0. So in the example, we come up with the truth table. We also have to include the clock here. Okay, so 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1. Okay, and if the clock is 0, basically your output is previous Q. So you don't really have to worry about all the different combinations of RS here, because if the clock is 0, in any case of RS, the combination of RS, the current output is the previous Q. Okay, so this is how it works. You can look into this timing diagram to see its output. Okay, so from this truth table, if you generate a map and simplify the map using the karnaugh map approach, you can obtain this boolean equation here. Okay, and again you can see that the current output depends on the previous output. Okay, so this is SR flip-flop. And next component is JK latch. So what is a JK latch? So as I previously stated, let's go back to the slide 45. JK flip-flop is SR plus toggle, and toggle is high to low, low to high, high to low, low to high, and it has two functions. One is set and reset, the other is toggle. So for this JK latch, we go to their truth table directly. Now, how do we do the toggle? In what situation we do the toggle? In the situation when both J and K are 1, we do the toggle. So it is here. When both J and K are 1, we do the toggle. For the situation here, it is the same as the SR latch. Okay, it is the same as the SR latch. So remember, in the previous SR latch, this is not allowed, right? But here in the JK latch, it is used for toggle. And so how does it work? You can look into this pseudo circuit and determine outputs. You just read this timing diagram. So the same, using this truth table, we can come up with a karnaugh map, and then we simplify, fill in the information, and then simplify the outputs, and then we can get this equation. Okay, so this is the JK latch. And the next device is the D flip-flop. So what is D flip-flop? Consider this data. This flip-flop is used to store the information of the previous output. So it works like a memory device, or say the data device. And this is a flip-flop. So in this diagram, pseudo circuit diagram, you can see there's a clock here. Okay, and this flip-flop, it is the output is memorized for at least one clock cycle. So it remembers your previous output Q. So this is the timing diagram. Also, you can come up with a the truth table, and in this truth table you only have one bit here, one input here, D, okay, and you have clock here, and this is age triggered clock. That means when the clock age here rise, the status of the output will change. Okay, when it is the change happens at rising age. Okay. Now I'm not going to the details either, and this is the truth table. Also, you can come up with a karnaugh map, and then you will see that your Q is equal to D. Q star is equal to D. Okay, and this is pretty much like how memory are created. And here on slide number 53, we can see the flip-flop, their schematic symbols. So for the SR latch, you have R, S as the input, and you have Q and Q, not Q, as the output. For the JK latch, you have J and K as the input, and Q and not Q as the output. And these are latches, so they don't work with clock. But for flip-flops, they work with system clock, and this symbol is the system clock. This symbol is the system clock. And so the JK flip-flop, you have J and K as the input, and for D flip-flop, you have D as the input. Okay, and what are these components or the circuits or chips really looks like? We have the TTL components here. We can see the quote SR latch. That means there are 4 SR latch in one chip. Quote means 4. Dual JK flip-flop with clock. Okay, so you have dual. That means with 2 JK flip-flop. Okay, and a dual D flip-flop with clock. Okay, and hex flip-flop with clock. Okay, so those are different TTL components that are available, and you can see that their parts number are here. So if you check the parts number, then you can find the right TTL component for you. Alright, so this is the summary of the flip-flops, and now we talk about SR latches used to set and reset. Your inputs, and we talk about JK flip-flop The JK means set, reset, plus toggle. And you have D flip-flops that is used to store data. And there are some other flip-flops, but I didn't cover them. And here is one more T flip-flop. Okay, it is the best for using the T flip-flop to build counters. Alright, so this is the unit that combinational logic and sequential logic I want to cover. And thanks for listening this course. And we will see you in another unit. Thank you very much. Bye bye.